Imagine a world without mountains of toxic battery waste. Sounds good, right? But the real problem is that our current battery recycling methods are often dirty, energy-guzzling nightmares. But what if there's a breakthrough that could change everything? A new method is emerging that could revolutionize how we reclaim precious materials from spent lithium-ion batteries, potentially solving a growing environmental crisis fueled by our insatiable demand for electric vehicles and gadgets. Researchers have pioneered a novel technique called flash Joule heating-chlorination and oxidation, or FJH-ClO for short, thankfully. This two-step process rapidly extracts valuable lithium and transition metals from used batteries. Think of it as a super-efficient way to dismantle batteries at the molecular level. But here's where it gets controversial. Traditional battery recycling is notorious for its reliance on harsh acids, copious amounts of energy, and the generation of significant wastewater. The FJH-ClO method, detailed in a recent Advanced Materials publication, flips the script. It's acid-free, energy-saving, and promises higher yields and purer materials like lithium, cobalt, and graphite. We designed the FJH-ClO process to challenge the notion that battery recycling must rely on acid leaching, states James Torr, a professor at Rice University and a key figure in the research. He emphasizes that FJH-ClO offers a fast, precise way to extract valuable materials without damaging them or harming the environment. The core issue is the explosive growth in lithium-ion battery usage. Electric vehicles are becoming increasingly popular, and our smartphones, laptops, and other portable devices are ubiquitous. This surge in demand inevitably leads to a mountain of discarded batteries, creating a pressing need for sustainable and efficient recycling solutions. Existing methods often fall short, struggling with high costs, inefficiencies, and the generation of harmful byproducts. The FJH-ClO process tackles these challenges head-on with its innovative two-step approach. First, battery materials are subjected to a brief, intense burst of heat in the presence of chlorine gas. This initial heating breaks down the complex battery structure, preparing the materials for the next step. Then, a second heating, this time in air, transforms most of the metals into oxides. And this is the part most people miss. Because lithium doesn't easily form an oxide, it remains as lithium chloride, which can then be easily dissolved and separated using water. In essence, it's like using a targeted heat treatment to selectively extract the valuable components, leaving behind the unwanted waste. The beauty of this method lies in its speed and precision, avoiding the need for prolonged chemical treatments. Tests have demonstrated the remarkable effectiveness of the FJH-ClO process. It can recover nearly all of the valuable materials from used batteries, including lithium, cobalt, and graphite, with exceptional purity. Early analysis indicates that, even on a small scale, this method may require approximately half the energy, a staggering 95% fewer chemicals, and significantly lower costs compared to conventional recycling techniques. These findings establish a scalable, acid-free pathway for comprehensively recovering lithium-ion battery materials. It offers compelling environmental and economic advantages, setting a new benchmark for sustainable battery recycling practices. For instance, consider the traditional method of hydrometallurgy, which involves dissolving battery materials in strong acids. FJH-ClO bypasses this messy and energy-intensive step entirely. This represents a huge step forward. It's rewarding to see a process that's both scientifically sound and practically useful, says Shirchin Su, the study's first author. That balance is what makes real-world impact possible. The FJH-ClO process has the potential to be seamlessly integrated into the existing battery supply chain. It provides a robust foundation for recovering valuable materials, thereby reducing our reliance on virgin mining, something that's crucial for long-term sustainability. The researchers are already taking steps to commercialize this groundbreaking technology. They plan to scale the process through their startup, Flash Metals USA, a division of Metallium Limited. This demonstrates their commitment to translating their research into a tangible real-world solution. This is more than just a lab experiment, Torr emphasizes. It's a blueprint for how the industry can meet the demand for battery materials without further straining the planet. The research received support from prestigious organizations such as the Defense Advanced Research Projects Agency, the Air Force Office of Scientific Research, and the U.S. Army Corps of Engineers, highlighting the significance and potential of this innovation. So, what do you think? Could this new method truly transform battery recycling? Are acid-free processes the future, or are there limitations we haven't considered? Share your thoughts and opinions in the comments below.